So in this video, I will be writing Python functions for calculating dew pressure, temperature, and bubble temperature pressure for a binary mixture of benzene and toluene. Then I will generate plots of the binary vapor-liquid equilibrium phase diagram at a constant temperature of 393 kelvins and another constant pressure of 150 kPa. So to start this off, I've already started with some imports and this wget our CHE tools. And then I imported NumPy. We're going to need SciPy root solver as well. And then obviously just importing our CHE tools and then Plotly in order to make our subplots. And then finally, I just imported the specific CHE tool props that we need of benzene and toluene. So the first thing that I'm going to do is just write out our mole fractions that we know. So I'm just going to put that in an array. And it's just like what I said here of 30% benzene, 70% toluene, so 0.3, 0.7. And then it'll just be the same thing for our vapor mole fractions as well. .3 and 0.7. So now the first function that we are going to define is going to be the bubble pressure. So I'm going to define a function for the bubble pressure. And again, we have to think about what we know, or what is given to us. So that'll be the mole fraction in the liquid phase and the temperature. And then what are we going to return? And that's pretty simple since we have already derived these equations. We're just going to be returning this here, our bubble pressure equation. So we can use NumPy sum, and it's going to be the sum of x times our pure saturation vapor pressure, which we can just use CHE tools for. So it'll be p.pvap. p.pvap, and it will be at our given temperature as well. So now we are going to get our function for the bubble temperature. So I'm going to define a function for the bubble temperature, and this time we'll be inputting our mole fraction and pressure, since that is what is known in this situation. So how we're going to do this is we are going to actually use the SciPy root solver, and how we're going to do that is using our bubble temperature equation that we derived in the last video. We can actually move this p to the other side and do 0 equals this minus p, and then we can use our root solver to find for what value of t does this all equal 0. So that's how we're going to find this bubble temperature. So obviously, in order to use the root solver, we're going to need another function. So we're actually going to have another function inside our bubble temperature function that we're going to use the root solver on. So I'm going to define another function. I'll just call it like EQ for equation. And in order to use the root solver, we have to input a vector into our function. And the first component of this vector is going to be our temperature, 0. And then what we will be returning is our function here that we are setting equal to 0, or our equation that we're setting equal to 0, which is just our bubble pressure equation, since this is equal to that, minus P. So we're actually going to have our bubble pressure function inside our return column here. So it's going to be something like the pressure minus our bubble pressure function for x, and then some value of t that we were trying to find. And then lastly, we have to use our root solver, and that's what's going to be in our return for the overall bubble temperature thing. So we're going to return, it'll be our root solver, and we are trying to solve the EQ equation. And then the last thing we have to do is just supply a guess, which we're just going to do like 273 Kelvin. And then, like every other time that we use the root solver, we're just getting the x component, the first value of that x component. So now we can work on getting our due pressure and due temperature equations, or functions. So it's basically going to be the same as our bubble temperature and bubble pressure, but instead of using our x, our mole fractions in the liquid phase, we're going to be using y, our mole fractions in the vapor phase. It'll be y and t, and then we will be returning, and we're going to use our equation for our due pressure right here that we derived in the last video. So it'll be 1 over numpy sum of y over p dot p vap at the temperature. Yes. And then we can do our due temperature as well. And that will again use our y mole fraction in the vapor phase, and this time our pressure. And we're going to be doing this just like we did our bubble temperature. So we're going to use our root solver, or SciPy root solver. And so we're going to have to define another function inside our function that we're going to be using the root solver on. So it's going to be exactly the same as what we did before. Like so. And then instead of returning using our bubble pressure function, we're going to use our due pressure function. So it'll still just be P minus our due pressure function for y t. And then again, we will be returning overall just our, this is what we're going to be using the root solver. And we're going to be using it on our EQ equation again. And then we need to supply a guess, and I'm going to do like 298. I'm actually going to do that for our other one too. I'm not sure if it really matters, but I feel like that's a better guess. And then again, get the x, the first component of the x. So now we have our Python functions for calculating our due temperature, pressure, and then our bubble temperature and pressure as well. So now we're going to work on actually plotting our different equations. So we're going to start off by doing our bubble pressure plot, and it's going to be at different mole fractions of benzene and toluene. So we're going to make we need a list of linear spaced mole fractions. And how we're going to do that is using numpy space. So we're just going to define x1 as numpy lin space and we have to say where we are going to be starting from, and it'll be from 0 to 1, from 0% benzene to 1%, and then we're going to want like 10 points, so I'm going to put 11 here. And then we are also going to need the mole fraction for toluene, which will just be the mole fraction that we just calculated, x1, 1 minus that. So like if this is 70%, this will be 30%. And then we can also define the temperature that we are at, which it told us was 393.15 Kelvin. So now using this temperature, we can get our vapor pressures, or our pure saturation vapor pressures, by doing P.PVAP at that temperature. And we're going to be storing that in the variable Psat. And now finally we can get our list of bubble pressures, which I'm just going to call list BP. And what that is going to be is we're going to use our equation here of the mole fraction times Psat. So it'll be x1 times Psat, and we're going to want it to be the first index, because this will be for our benzene, which is the first index in our thing here for CHE props. And then we're going to do the same thing for our toluene. It'll be x2 times Psat. This time the index will be 1. So now we can plot this up. So we're going to do fig equals make subplots, and we're going to want 1 row and 2 columns, and then we'll just add the scatter, fig.add underscore scatter, and our x values will just be our mole fractions, x1, and our y values will be our bubble pressure list. And we're going to want this in row 1, column 1. There we go. Now we are going to work on plotting our dew pressure. So again, we're going to need a list of the dew pressures that we will be plotting. And we're going to start off just with a blank list. And we're just going to append onto that our dew pressures. So we're going to need our mole fractions, but this time in the gaseous phase, so that'll be y1. And it's going to be in the same range as x1. So we can say something like for y1 in x1, then our y2 is going to equal 1 minus y1. And that will be getting us our mole fractions for our dew pressures. And how we are going to get these dew pressures that we'll be appending onto this list is using our dew pressure function up here. And we need to input an array, as you can see here, into our dew pressure function. So we're going to want to make an array of our mole fractions. So I'm just going to do that manually. Numpy array. And it's just going to be our y1 and y2. And then we can append onto our list append, I think it's a list.append, list.append list.dp.append, yeah. And then that's where we're going to use our dew pressure function, dp of y and t. So now we can plot this, and it's going to be on the same plot as our bubble pressure, but instead it's going to be our dew pressure. Like so. So now we are going to work on plotting our dew temperature and bubble temperature. And we're going to be doing it a lot like how we got our dew pressure. So we're going to have two lists, a list for our bubble temperature and a list for our dew temperature. And they're going to start empty, and we're going to be using a for loop again to append onto them. So that for loop is going to be using our mole fractions again. So, but these mole fractions are going to be different, so I'm going to call them Z1, but it's still going to be in the same range. And then obviously we can calculate Z2 as 1 minus Z1. As well. So now we can start appending to our list. So list the bubble temperature, and we're going to append onto that. And we're going to append using our bubble temperature function up here. So the bubble temperature function. And we're going to have to input our mole fractions and pressure into that. So first we need to define our pressure, which was actually given to us in the problem as 150 kPa, which will be 1500 pascals. So that'll be the pressure that we'll be putting into here. And then for our mole fractions, it's just going to be an array of our Z1 and Z2. And then we're just going to do that again. But this time for our dew temperature, using our dew temperature function. Now finally, we can plot this up, just using the same thing as we did before, but the x's are still going to be x1, but this time the y, we're going to be wanting to do the bubble temperature and the dew temperature. And then we want it in column 2. I'm just going to run all to make sure that this works. And there we go. Those are our two plots. And I'm actually going to give these names as well. Name. So this will be our bubble pressure. This will be our dew pressure. This will be our bubble temperature. And this will be our dew temperature. Like so.